So in the previous lecture, we discussed the continuous functional calculus in Sistar algebras. And today, our first goal will be to apply the functional calculus to the study of positive elements in Sistar algebras. So we give the following definition. Suppose that A is a Sistar algebra and little a is an element in our algebra. We say that our element is positive and write the following symbol. If it is self-adjoint, and if the spectrum of this element is non-negative. Well, formally, we don't assume that A is unital, so we must take the non-unital spectrum here. However, it's easily seen that if A is unital, then we can replace the non-unital spectrum by the usual spectrum here. If A is unital, then this last inclusion is equivalent to the inclusion of the usual spectrum in the positive half line. And the reason is that we remember that if A is a unital algebra, then the only difference between the spectrum and the non-unital spectrum is 0. Okay, so this is our definition. Probably it would be more correct to call such elements non-negative elements, but nevertheless, this is the standard terminology. Let's look at the following basic example. Suppose that A is C0 of x, the algebra of continuous and vanishing at infinity functions on a locally compact Hausdorff space X. Then an element of our algebra is positive in the sense of the above definition, if and only if this function is non-negative everywhere. Well, indeed, if, for example, X is compact, then we know that the spectrum of A is just the range of A. And in the case where X is locally compact, we know that the spectrum is the union of the range and 0. And so it is positive in the sense of the above definition, even only if it is non-negative everywhere. So morally self-adjoint elements of a Sistar algebra should be considered as non-commutative analogs of real functions. And positive elements of a Sistar algebra should be considered as non-commutative analogs of non-negative functions. So this is the idea. It will be convenient to introduce a special notation for the set of all positive elements. So the set of all positive elements of A will be denoted like this. We have the following simple result. This is proposition 1. First of all, suppose that phi is a star homomorphism between Sistar algebras A and B. A and B are Sistar algebras. Then phi takes positive elements to positive elements. And second, which is actually a special case of the above result, if little a is a normal, if our algebra is unital, if A is unital, and little a is a normal element for our algebra, and f is a continuous function on the spectrum, which is non-negative everywhere on the spectrum, then the element f of a is positive. So if we apply a non-negative function to a positive element, we get a positive element. The proof is very easy. First of all, if little a is a positive element, so we know that, of course, each positive element is self-adjoint by definition. So phi of a is also self-adjoint. Clearly, star homomorphism takes self-adjoint elements to self-adjoint elements. And the spectrum of phi of a is always contained in the spectrum of A. This is the general property of homomorphisms between algebras. And so it is non-negative. And that's it. So this implies that phi of A is positive. And part 2 is actually a special case of part 1. We simply apply part 1 to the functional calculus. So the functional calculus of A is a star homomorphism from the algebra of continuous functions on the spectrum to A. And it takes non-negative elements to non-negative elements. So since f is non-negative, we conclude that gamma of f, which is the same as f of a, is positive. Okay, let's now look at some properties of the set of positive elements. This is our proposition 2. First of all, I claim that if little a is a positive element and lambda is a non-negative real number, then lambda a is also positive. Second, we have the following quality. Which means that if we have an element little a, which is positive, and is such that minus a is also positive, then our element is 0. Property 3, the set of positive elements is closed in A. And finally, I claim that the sum of two positive elements is also positive. So these properties together mean that the set of positive elements is a closed convex cone in A. Closed convex cone in A. Well, to prove this result, we need a simple but useful lemma. Suppose that A is a unit of Sistar algebra. Little a is an element in our algebra such that the norm of A is less than or equal to 1. Then I claim that A is positive if and only if A is self-adjoint and the norm of 1 minus A is less than or equal to 1. So basically, this is an equivalent definition of a positive element, which doesn't involve spectrum. It doesn't involve the spectrum of A. To prove this result, we first observe that the result is clear if A is the algebra of continuous functions on a compact topological space. Well, indeed, in this case, A is a function. Of course, we can assume from the very beginning that it is self-adjoint. So it's a function whose values are between -1 and 1. And such a function is positive if and only if 1 minus A is less than or equal to 1 everywhere. So this is a special case, but in fact, this special case covers all possibilities, because in the general case, we consider the Sistar subalgebra of A generated by our element little a and the identity of A. So this is a commutative unit of Sistar algebra, and we can apply the First-Gelfand-Leinberg theorem to this subalgebra. So this algebra is isomorphic, isometrically star isomorphic to the algebra of continuous functions on the maximal spectrum. And so everything is reduced to the case where A is just C of X. Okay, so this completes the proof of our lemma. And now we are ready to prove the proposition 2. First of all, part 1 is clear from the definition. If we look at the definition of a positive element, it's clear that the set of positive elements is stable under multiplication by non-negative numbers. Okay, now property 2. If little a is in this intersection, so we want to show that this intersection is 0. So if little a is in this intersection, this means that A is positive and minus A is positive. So the spectrum of A is contained in, on the one hand, it is contained in the non-negative half line and in the non-positive half line. So this means that the spectrum of A is 0. The spectrum of A is 0. But our element is self-adjoint. And for a self-adjoint element, the spectral radius equals the norm. So if the spectrum is 0, this means that the spectral radius is 0, and so the norm is 0. So our element little a is 0. And this proves part 2. And now we prove parts 3 and 4. So we want to show that the set of positive elements is closed. It's closed, and the sum of two positive elements is positive. And here, this is the place where we need our lemma. So let bold B denote the closed unit ball of our algebra. Then our lemma implies the following equality. So this equality is just an equivalent form of our lemma. So look, if we have an element in the unit ball, then it is positive, that is, belongs to this intersection, if and only if it is self-adjoint, and 1 minus a is less than or equal to 1. So here we have to work in the unitization because we don't assume our algebra A to be unital. So our lemma is equivalent to this formula. But now this formula readily implies that well, let's look at the right-hand side of this formula. So each set in this each set here is closed and convex. This is the unit ball. Clearly, it is closed and convex. The set of all self-adjoint elements is, well, it's a closed real vector subspace. So it is also closed and convex. And the last set is, again, a closed ball centered at the identity. So it is also closed and convex. So this equality implies that the intersection of the unit ball and the set of positive elements is closed and convex. But it's a simple exercise to show that this implies that so is a set of positive elements. Okay. So these are the basic properties of the set of positive elements. A useful property of positive elements is that each positive element has a unique positive square root. This is our next result, proposition 3. Well, before I formulate the proposition, let's introduce some natural notation. For each positive element A in our algebra, we define the square root of A by means of the functional calculus. So we apply the square root function to A. F of t is the square root of t for all non-negative real numbers t. So this is well defined because f is defined on the non-negative half line, and in particular it is defined everywhere on the spectrum of A. So we can take the square root of A. What can I say about this element? This is our next proposition, proposition 3. The square root of A is a unique positive element, a unique positive element of A, satisfying the following identity. First of all, why is it positive? It is positive by our first proposition. The square root is a non-negative function, and when we apply a non-negative function to a normal element, we get a positive element. Now let's recall the superposition property for the functional calculus. So if we apply it to two functions, square root and square, we see that if we first take the square root and then take the square, we get a. The superposition property in general states that if we have two functions f and g, so f is a continuous function on the spectrum of A, and g is a continuous function on the spectrum of f of A, then if we first apply f to A and then apply g to f of A, the result will be the same as if we first compose g and f and then apply it to A. So this is the superposition property. And here we apply it to the square root function and to the square function. Okay, so why is it unique? Well, so suppose that B is another element, another positive element, such that B squared equals A. And again, we apply the superposition property. Essentially to the same functions, but composed in the opposite order. And we conclude that B equals the square root of B squared. That is to the square root of A. And this proves the uniqueness. Okay. Here are two simple but useful applications, or two simple exercises. Exercise 1 is a useful characterization of positive operators on a Hilbert space. So suppose that H is a Hilbert space. And we consider the algebra of bounded linear operators on H. So if T is a bounded linear operator on H, then T is positive as an element of our Sistar algebra B of H, if and only if the respective quadratic form is non-negative everywhere. And another illustration, exercise 2. If A is a unit of Sistar algebra, then every element of our algebra is a linear combination of 4 unitaries. Of 4 unitary elements. And here's a hint. The hint will be a little picture. So this is a circle. This is T. This is alpha. And this is beta. And the hint is the following formula. T is alpha plus beta over 2. Okay. Another useful property of positive elements is the following. This is proposition 4. For each self-adjoint element in our Sistar algebra A, there exists a unique pair, A plus and A minus, a unique pair of positive elements such that A equals A plus minus A minus, and such that the product of A plus and A minus taken in any order is 0. Before we prove this result, let's observe that if A is the algebra of continuous functions on the compact Hausdorff space, then the result is more or less clear. So here's a picture. If, say, this is the graph of our function A, this is a real function, so we can decompose it as the difference of two non-negative functions as follows. So this is the first function, the graph of the first function. And this is the graph of the second one. In the general case, the proof is more or less the same. It uses the functional calculus trick. We consider the following two functions. T plus and T minus. I'll not write explicit formulas, I'll just draw a picture. So I hope it will be clear what the functions are. So this is the graph of T plus. And here's the graph of T minus. It is 0 here. And it looks like this for negative numbers. This is T minus. By the way, they are not just real, they are non-negative. And let's observe now that if we define A plus and A minus by the following formula, then these elements are exactly what we need. Well, indeed, they are positive because the functions T plus and T minus are positive. So A equals A plus minus A minus because T plus minus T minus is the identity function of the real line. And the product is of A plus and A minus is 0 because the product of T plus and T minus is 0. So the functional calculus is an algebra homomorphism. So to complete the proof, we have to show that such a pair is unique. Okay, suppose that we have another such pair. Suppose that A1 and A2 are positive. A equals A1 minus A2, and their product is 0. So we want to show that A1 equals A plus and A2 equals A minus. So let's introduce some notation. We denote by the absolute value of A the sum of A plus and A minus. So equivalently, this is the absolute value function applied to A. And we do a little calculation. So A squared is A1 minus A2 squared. If we calculate it explicitly, it will be A1 squared plus A2 squared, A1 squared plus A2 squared. Because the product A1, A2 and A2, A1 is 0. And for the same reason, this can be written as A1 plus A2 squared. but the same result holds with for a plus and a minus. So for the same reason, this is a plus plus a minus squared. That is the absolute value of a squared. And now we compare these two elements, this one and this one. So they are the same and they are positive. So we take the square root. Take the square root, and we conclude that a1 plus a2 equals the absolute value of a. And if we now combine this formula and this formula, so the difference is a, the difference of a1 and a2 is a, and the sum is the modulus of a. So as a result, we see that a1 is given by the following formula, and this is nothing but a plus. And similarly, a2 is given by the following formula. This is nothing but a minus. And this proves the uniqueness of our pair and plus and a minus. Okay. Our next result is probably one of the most fundamental properties of positive elements. So we have the following theorem due to Kaplanski. The theorem states that for each element in our Sistar algebra, the element a star a is positive. Historically, this theorem was not a theorem, but it was an axiom. So it was one of it was a part of the definition of a Sistar algebra. But it wasn't clear if this axiom is really needed. And the fact that this axiom can be proved, can be deduced from other Sistar algebra axioms, was proved only by Kaplanski in the 1960s. That is about 20 years after the introduction of Sistar algebras by Gelfand and Naimark. The proof will be based on a couple of lemmas. Lemma 1. I claim that for each element x in our algebra, x star x plus x star is positive. To prove this result, we decompose x as y plus iz, where y and z are self-adjoint. Well, then we take the star. We see that x star equals y minus yz minus iz. So x star x is, what is this? This is y squared plus z squared plus I multiplied by yz minus zy. And similarly, x star equals y squared plus z squared plus I multiplied by zy minus yz. So the sum of these two elements, x star x plus x star, is 2 times y squared plus z squared, and the remaining terms cancel. So these two terms cancel. But this element is positive. well, y squared and z squared are positive because the square function is everywhere positive. So this follows from proposition 1. And the sum of two positive elements is positive, and when we multiply them by 2, the result is still positive. So this follows from propositions 1 and 2. Okay. Lemma 2. Lemma 2 is purely algebraic. Suppose that A is a unital algebra. Just an algebra without any norm, just a unital algebra. And A and B are two elements of A. I claim that the spectrum of AB is almost the same as the spectrum of BA. Or more exactly, we have the following identity. So in other words, the only possible difference between these two spectra is 0. To prove this lemma, it suffices to show that that 1 minus AB is invertible, even only if 1 minus BA is invertible. Just because in the general case, for an arbitrary non-zero number lambda, for each non-zero number lambda, we can write AB minus lambda as minus lambda multiplied by 1 minus lambda inverse AB. So the invertibility of this element is reduced to the invertibility on 1 minus lambda inverse AB. Okay. So if we now assume that 1 minus AB is invertible, and let C denote the inverse of this element, then a direct calculation shows that 1 plus BCA is the inverse of 1 minus BA. So 1 minus BA is invertible. Well, of course, it's a kind of trick. So perhaps it's appropriate to explain where this trick comes from. Well, here's an informal explanation. Let's write 1 minus AB as the following infinite sum. 1 plus AB plus AB squared, and so on. So this is just a formal expression, and I don't claim that the series always converges. And moreover, our algebra A is not equipped with any topology. So we only know that this formula is true if we work in a Banach algebra and our elements A and B are small enough. But anyway, this helps. So what is this? This is 1 plus AB plus AB, AB, and so on. So this is 1 minus AB, AB inverse, of course. I'm writing the inverse element of 1 minus AB. So if we try to do the same for 1 minus BA, the result will look as follows: 1 plus BA plus BA, BA plus BA, 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 and so on. And we do the following. This is 1 plus, so B multiplied by something and multiplied by A. And what is something? This is 1 plus AB plus A, B, and so on. And this is our element C. So this explains where the above proofs comes from. So we just guess what the inverse of 1 minus BA is, and we check that this element 1 plus BCA is indeed the inverse by multiplying this element by 1 minus BA. Okay, so now we are ready to prove Kaplanski's theorem. So let's recall the statement. We want to show that for each element little a in our Sistar algebra A, the element A star A is positive. Well, let's denote this element by B. B is A star A. And we write it as in our previous proposition. So B is B plus minus A minus. So clearly B is self-adjoint. So we can write it in the following form, where B plus and B minus are positive, and their product is 0. So we want to show that B minus equals 0. In this case, this will mean that B is positive. So we do the following trick invented by Kaplanski. We'll let X denote the element AB minus. So what can I say about X star X? X star X is B minus just a moment. Yes, okay. B minus A star, A, B minus. So what is A star A? A star A is B, and B is B plus minus B minus. So this is B minus times B plus minus B minus, and again by B minus. Now, since the product of B plus and B minus is 0, we see that this is just minus B minus cubed. And this implies that the element minus X star X is positive, because it is equal to B minus cubed. Okay. Let's now look at the element from lemma 1, X star X plus X star. So we know that this element is positive. So we can write this element in the following way: X star X plus X. Maybe let's do it in a slightly different way. So we look at XX star. So XX star is X star X plus XX star plus minus X star X. This is obviously true. But what can we say about these two elements? Well, the first one is positive by lemma 1. And we have just shown that the second element is also positive. So their sum is positive. So XX star is positive. And now we apply lemma 2. We apply lemma 2 to the elements XX star and X star X. And we conclude that X star X is also positive. But we have just seen that minus this element is positive. So this can happen only if this element is 0. Okay, now this element is 0, but we already know that this element is equal to minus b minus cubed. So we see that b minus cubed is 0. And after taking the cube root, we conclude that b minus is 0. But this is exactly what we wanted to show. So this completes the proof. So the proof is short, but is quite tricky. So it's impossible to guess how Kaplanski get this idea. But anyway, the result is true.
Because we've also proven that x star x is 0, right?
Yeah. Yeah, x star x is 0, but well, this is true. But what we really needed to prove that b minus is 0, and so we see that b minus is indeed 0. Okay. As an application of this theorem, we can now define the absolute value of any element in our Sistar algebra. So we introduce the following notation. For each element A in our algebra, we define the absolute value of A to be the square root of A star A. So we know now we know that A star A is positive, so we can take the square root and we get a positive element in our algebra. By the way, let's observe that this notation is consistent with the functional calculus. Namely, if our element Lily is self-adjoint, then the absolute value that we've just defined is the square root of A squared. And by the superposition property, this is the absolute value function applied to A. Or if we use notation from proposition 3, we see that this is A plus plus A minus. But the point is that now the absolute value is defined for each element of our algebra that is not necessarily a self-adjoint element. As another application, we get the following corollary, which characterizes positive elements. If A is an element in our algebra, then the following conditions are equivalent. Condition 1, A is positive. Condition 2, there is a positive element B such that A equals B squared. Condition 3, there is a self-adjoint element B such that A equals B squared. And finally, condition 4, there is an element B in our algebra such that A equals B star B. Well, indeed, the equivalence of these conditions readily follows from Kaplanski theorem, when indeed one implies 2. To see that one implies 2, we just take the square root. It's clear that 2 implies 3 and 3 implies 4. And finally, if we apply Kaplanski's theorem, we see that 4 implies 1. So all the 4 statements are equivalent. Okay, now we apply the positivity to introduce a useful order relation on the self-adjoint elements of a Sistar algebra. So we give the following definition. you have two self-adjoint elements, A and B, in our algebra, then we say that A is less than or equal to B if B minus A is positive. In fact, this definition can be extended to arbitrary elements, not necessarily self-adjoint, but traditionally it is introduced only for self-adjoint elements. We have the following result, the following proposition, which describes the properties of this relation. First of all, I claim that the set of all self-adjoint elements equipped with this order relation is indeed a partially ordered set, PO set. PO set is the abbreviation for partially ordered set. Property 2, if A is less than or equal to B, and lambda is a non-negative real number, then lambda A is less than or equal to lambda B. So the order relation is compatible with multiplication by non-negative numbers. Property 3, the order relation is compatible with the sum operation. Namely, if A1 is less than or equal to B1 and A2 is less than or equal to B2, then A1 plus A2 is less than or equal to B1 plus B2. Property 4, if A is less than or equal to B and X is an arbitrary element in our algebra, then X star AX is less than or equal to X star BX. Looks a bit technical, but this is very convenient, as we will see. Property 5, if our algebra is unital and little a is an element of A such that A is greater than or equal to 1, the A inverse is less than or equal to 1. Property 6, it generalizes property 5, namely if A is unital and we have two elements of A, little a and little b, such that they satisfy the following relation, and both A and B are invertible. I claim that in this case, B inverse is less than or equal to A inverse. Property 7, if A is less than or equal to B, and both of them are positive, then the norm of A is less than or equal to the norm of B. So the order relation is compatible with the norm. And finally, property 8. Well, maybe property 8 should be property 7. So let's just a moment. Let me recall the proof. Oh no, that's okay. Property 8. So if little a is a positive element in our algebra, then the norm of A is less than or equal to 1, if and only if A is less than or equal to 1 in the unitization of A. And if A is unital, then we can replace the identity of the unitization by the identity of the algebra A. So if A is unital, then it happens if and only if A is less than or equal to 1. Okay, so these are the basic properties of our order relation on the self-adjoint elements. The proof is indeed shorter than the statement. Let's look at properties 1, 2, and 3. And let's observe that 1, 2, and 3, they follow from the respective properties of the set of positive elements. So it's a pose set. For example, our order relation is transitive because the sum of two positive elements is positive. For the same reason, we have property 3. And property 2 follows from the fact that the product of a positive element by a non-negative number is positive. So 1, 2, and 3 follow from proposition 2. Okay, now part 4. Part 4. We take our element b minus a, which is positive by assumption, and write it in the form c star c for some c and a. Actually, we can take, for c, we can take the square root of b minus a. And we look at the difference x star bx minus x star ax. So we want to show, there's the statement, we want to show that this difference is a positive element. Well, what is this? This is x star multiplied by b minus a, and b minus a is c star c, multiplied by x. And this is nothing but cx star cx. And now Kaplanski's theorem implies that this is positive. Okay, so this is part 4. Part 5 readily follows from part 4. Namely, we apply 4 to the following element x, a to the power 1 minus 1/2, and we get 5. So 1 is less than or equal to a. We multiply by a to the power 1 minus 1/2 on both sides, and we get that a inverse is less than or equal to 1. Okay, now property 6. Well, a and b are positive and invertible. We want to show that if a is less than or equal to b, then b inverse is less than or equal to a inverse. Well, let's multiply both parts by a to the power minus 1/2. So we see that 1 is less than or equal to a to the power minus 1/2, b a to the power minus 1/2. So here we used property 4. And now we apply property 5 to this element. So property 5 implies that this element, the inverse of this element, is less than or equal to 1. And the inverse of this element is given by the following formula. So this is less than or equal to 1. And finally, if we apply 4 again, but now with a to the power minus 1/2, we get that b inverse is less than or equal to a inverse, which completes the proof. Property 7. If a is less than or equal to b, then the norm of a is less than or equal to the norm of b. Okay, we do the following. We apply the Gelfand-Naimark theorem twice. First, we apply the Gelfand-Naimark theorem the first Gelfand-Nymark theorem. To the Sistar subalgebra of A generated by B and the identity. This is the Sistar subalgebra of the unitization of A. This is a commutative Sistar algebra, a commutative unital Sistar algebra, and B is an element that is a continuous function. So obviously this implies that B is less than or equal to the norm of B multiplied by the identity. Okay, now let's recall that A is less than or equal to B. So this implies that A is less than or equal to the norm of B multiplied by the identity. And now we apply the Gelfand-Nymark theorem again, but to the Sistar subalgebra generated by A and the identity of A plus. And we conclude that, well, A is a function which is between 0 and some constant. And so the norm of this function is less than or equal to the same constant. And this is exactly what we wanted to prove. Well, and finally, property 8. Well, property 8 is again immediate from Gelfand-Nymark theorem. So since we have three statements about a positive element, we can just consider the Sistar subalgebra generated by this element and the identity. But for the algebra C of X, the result is clear. So part 8 also follows from the Gelfand-Nymark theorem applied to the Sistar subalgebra generated by A and the identity element. Or in the unital case, we can take the Sistar subalgebra of A generated by A and the identity of A. And the result will be the same. Okay, so this completes the proof of our proposition. Our next goal is to discuss approximate identities in Sistar algebras. Well, we have already seen that there are many natural examples of non-unital Sistar algebras. Maybe this is not very convenient, but, well, that is life. Of course, we can always add and join an identity to our algebra. We can consider the unitization, which is also a Sistar algebra. And sometimes this solves all our problems. But nevertheless, there are some situations in which we are forced to work with the original non-unital Sistar algebra. And roughly, the notion of an approximate identity is a useful analytic substitute for the identity, which doesn't always exist. Okay, so before we define approximate identities, let's discuss some basic facts from general topology. So suppose we have a partially ordered set, lambda. Pose set. We say that lambda is directed if for any two elements in the set, lambda and mu, there is another element which dominates both lambda and mu. In Russian, directed is направленное множество. Here are two basic examples to keep in mind. The obvious example is the set of natural numbers with the standard order relation. Obviously, it is a directed set. And another example is the following. Let lambda denote the set of all neighborhoods of a fixed point in a topological space. So here big X is an arbitrary topological space. And the order relation is the reverse inclusion. In other words, a neighborhood is bigger in the sense of our order relation if it is smaller as a set. So obviously it's a directed set, because if you have two neighborhoods of the same point, we can just take their intersection, which dominates both the neighborhoods. Okay. So now suppose that X is a topological space. By definition, a net X is a map, say little x, from a directed set lambda to X. So here, lambda is a directed set. Direct poset. In Russian we usually say, мы обычно говорим не сеть, а направленность. Такая терминология, может быть, даже более удачная, чем слово сеть. Непонятно, при чем тут сеть, а направленность как раз понятно, почему они так называются. Morally, a net is a generalized sequence. So to emphasize this analogy, we introduce the following notation. We think of a net as a family of elements indexed by a poset lambda. So instead of writing x of lambda, we will write just x lambda, to emphasize this analogy between nets and sequences. The convergence of nets is defined in exactly the same way as the convergence of sequences. So we say that a net x lambda converges to a point little x and we write the following sequence of symbols, or sometimes we say that the limit of this net equals x if for each neighborhood u of x there is an element lambda 0 in our set, such that for all elements that are bigger than lambda 0, the respective elements x lambda are in the same neighborhood u. So clearly this is the same as the convergence of sequences. If big lambda is a set of natural numbers with the usual order relation, then we get just the definition of a convergent sequence. And here's a useful example. So let lambda be the poset from our previous example. So this is a set of all neighborhoods of a point in a topological space. So for each neighborhood U, for each element U in lambda, let's choose an arbitrary point in this neighborhood. Choose any point x u in this neighborhood. Then it's easy to see that the net xu converges to x. This is immediate from the definition. So if we take for lambda 0 the same neighborhood u, then of course for all elements which are for all smaller neighborhoods, the respective points are in the same neighborhood u. So the net converges to x. Okay, so these are some definitions from general topology, and now let's come back to Banach algebras, and let's introduce the notion of an approximate identity. So from now on, we suppose that A is a normed algebra. By definition, an approximate identity AI for short. And A is a net E lambda in A such that for each element A in our algebra, the net A E lambda converges to A, and E lambda A converges to A. And let's also look at following two special properties. Property 1, we say that an approximate identity E lambda is sequential if lambda is the set of natural numbers, and the order relation is the usual order relation on the natural numbers. So in this case, an approximate identity is just a sequence. And second, we say that an approximate identity E lambda is bounded if the set of all elements in this net is bounded. So that is, there exists a constant C such that the norm of each E lambda is less than or equal to C. Well, our main result will be that each Sistar algebra has a bounded approximate identity. Today, we don't have time to prove this. So in conclusion, let me just give you some examples of approximate identities. Example 1. Let A be the little C0 algebra, which is the same as big C0 of N. So this is the algebra of all sequences which vanish at infinity. And for each natural number n, let En denote the following sequence, the following element of our algebra. It's a finite sequence, so it sits in our algebra. So I claim that this sequence is a bounded approximate identity. BAI is a standard abbreviation for the bounded approximate identity. Well, indeed, why is it so? If we take an arbitrary element A in our algebra and calculate the norm of A minus AEN, this will be the supremum of AK, where K is bigger than N. And this goes to 0 because A vanishes at infinity. So it's a bounded approximate identity. Example 2. Example 2, let A be the little L1 space. And we considered it as a Banach algebra with pointwise multiplication. Then I claim that the same sequence En from example 1 is an unbounded approximate identity. So clearly it is unbounded. The norm of En, the L1 norm of En equals N. And the same argument as in example 1 shows that it is an approximate identity. So it is unbounded. Now, an actual question is, maybe there is another approximate identity in little L1 which is bounded. But the answer is no. This is a useful exercise. L1 doesn't have a bounded approximate identity. Example 3, which generalizes example 1. Well, not generalizes, but is similar to example 1. Let A be the algebra C0 on the real line, the algebra of continuous vanishing at infinity functions on the real line. And let's define the function En as follows. So I'll just draw a picture. This is 1. This is N and minus N. And here we make it just piecewise linear. So this is En. So it's a simple exercise to show that En is a bounded approximate identity. Well, the proof is essentially the same as in example 1. In fact, this can be easily generalized to an arbitrary locally compact space. Example 4. Let A be the algebra C0 of X, where X is a locally compact Hausdorff topological space. And let lambda denote the set of all compact subsets of K of X. So lambda is a directed poset with respect to the usual order relation. So the order relation is just the inclusion. This is a directed poset. It is directed because if you have two compact sets, then the union of their union is also compact. Now for each compact set K, we choose a function ek in C0x such that this function is identically 1 on K, and such that the norm of ek is less than or equal to 1. Such a function always exists by Urysohn's lemma. I claim, and this is an exercise, that the respective net, ek, where k runs over lambda, is a bounded approximate identity. This is an exercise. Okay, our final example concerns the algebra of compact operators. Or by the way, one more remark concerning example 4. Of course, this approximate identity from example 4 is not sequential. So in example 3, we have a sequential approximate identity. In example 4, the approximate identity is not sequential. And here's useful exercise. C0x has a sequential approximate identity. Even only if x is sigma compact, which means that x is a countable union of compact subsets. Okay, and finally, let's look at the algebra of compact operators on a Hilbert space. This is example 5. A is K of H, where H is a Hilbert space. Of course, we know that this algebra is not unital unless H is finite dimensional. On the other hand, it always this algebra always has an approximate identity. And to construct it, let's denote by lambda the set of all finite dimensional subspaces. Finite dimensional subspaces of H. This is also a directed pose set, and the order relation is just the inclusion. If we have two finite dimensional subspaces, then their sum, the algebraic sum, is also finite dimensional. This implies that this pose set is directed. Now, for each finite dimensional subspace of H, let PL denote the orthogonal projection onto L. So it's a compact operator because it is a finite rank operator. I claim, and this is again an exercise for you, that the respective net, PL, where L runs over lambda, is a bounded approximate identity in K of H. Again, this approximate identity is not sequential. So another useful exercise is to show that K of H has a sequential approximate identity, even only if H is separable. Well, and in conclusion, probably it's appropriate to look at a counterexample, which shows that there are Banach algebras which don't have approximate identities. This is example 6. First of all, we have a trivial example. If you take any normed space or any Banach space A, and equip the space with a zero multiplication. That is, the product of any two elements is zero. Of course, it's an algebra. It's not unital, but it's an algebra. And this algebra doesn't have an approximate identity. For obvious reasons. The product of any two elements is zero. And here is a more interesting example. Let A be the maximal ideal of the algebra of continuously differentiable functions on an interval. So this is the algebra of those C1 functions on the interval 0, 1, such that f vanishes at 0. I claim that this algebra doesn't have an approximate identity. This is also a simple exercise for you. Okay, so that's all for today. And at the next lecture, we begin by showing that each Sistar algebra has a bounded approximate identity, which also has a bounded approximate identity with some special properties. This is a very useful result. Okay, thank you.